Hello there.
Hello, how are you?
I'm doing alright. How about you?
I'm doing fine. I just passed my exams today.
Nice.
Yes,
That's
yeah,
nice to hear.
yeah. Let me connect to
Mm,
my hotspot so then I don't lag.
alright. I see that you are lagging a lot, you know. You are lagging a lot.
Yeah, yeah. I like a lot sometimes.
Yeah.
Mhm. Wait, let me see what's going on here.
And it's gonna be an organic chemistry class because someone else is in here, you know.
Yeah, yeah. We'll go over organic chemistry in this office hours.
Yeah. I still participate though, even though I don't know anything about organic chemistry.
Yeah, yeah. But you will soon once you get to that point. Like you
Yeah,
know.
yeah, yeah, I know.
Yeah.
I have learned the Lewis thing. I forgot the name.
Hmm.
I learned that
High,
too.
high school chemistry. Like you're starting that.
Yeah, I'm
You're
starting
starting
the
to
high
learn.
school chemistry thing. Yeah.
That's good. What are you learning right now? Like the elements, periodic table, protons, neutrons, electrons.
Well, mostly periodic table, but
Yeah,
also
periodic table.
proton, neutrons, and that stuff.
Right. Like the chart of like the letters
Yeah,
and
the
everything, what they
SAS,
mean.
the cations, anions, and that stuff.
Mm-hmm. Right. See. Let me connect to the Zoom on my iPad. Is it making sense? Like the high school chemistry so far?
Yeah, it makes sense. I'm understanding it.
That's good. That's good. Okay, so in this session
Recording in progress.
go over the last four problems of the problem set, um, and how to get those answers. Right.
All right.
So yeah. Right. Let's see. Uh, where's my keyboard here? Oh, there it is. Notes. Okay. Shared over here. There we go. Okay. And let me go all the way down. Boom. Okay. Share screen. Right. 21, 20, 19, and 18. Okay. Let's do 18, 19, 20, 21. Okay. Oh, so this is the electrocyclic reaction with con-rotatory, this rotatory stuff. There is a table that goes with this to tell whether you have a con-rotatory or dis-rotatory reaction, and then you could use your thumbs to figure out the stereochemistry of this reaction, right? But I remember the table going something like this, where um, depending on how many electrons you have in the electrocyclic reaction, either 4n plus 2, or the way I like to think about that is an odd pair of electrons or 4n electrons, or an even pair of electrons. Right. 0, 1, 2. That's right. Let's see. Right. 2, 4, 6, 0. Okay, and then that's even pair. That's 2, 4. Yeah, okay. Right, and then you could either have this reaction happening under heat or light, right? And depending on if you have heat or light, you're either going to be in the con-rotatory or dis-rotatory conditions for this reaction, right? But I can't remember like what it is. Let me check the chart I made last time for this chart here. But right now my guess is con, this, con. Wait, let me double check this real quick. When did I make that? Spring. Electrocyclic reaction, CR10. Oh, here. Okay. So it's gonna be the other way around. This is gonna be flipped, right? The even pair of electrons are gonna be the first row. The odd pair of electrons is gonna be the second row, and that's important to know for this reaction, right? Where con-rotatory will mean that you are going to rotate the groups in the same direction. Right? And the direction is either going to be clockwise or counterclockwise. So that's con-rotatory. For dis-rotatory, it's the opposite. You're going to rotate the groups in opposite directions. And the directions is going to be in terms of clockwise or counterclockwise. Rotatory. Opposite direction. Right? And you could use something called the thumb rule to help you predict the stereochemistry of this reaction, right? Because this electrocyclic reaction here can either be a ring closing reaction or a ring opening reaction, right? And I'll tell you how to figure out what kind of reaction you have depending on what the starting material is. But you could either have a ring closing reaction or a ring opening reaction, right? And depending on what kind of reaction you have, you're going to start your thumbs in a certain way to predict what the stereochemistry is going to be in the product. Right. So if you have a ring closing reaction, you're going to start your thumbs either left or right. And then you're going to end your thumbs up or down, right? And ring opening is the opposite. You're going to start your thumbs up or down, and then you're going to end your thumbs left or right. Right? And I'll show you like what this means for a reaction in, let's say, this problem here, right? But we're going to rotate clockwise or counterclockwise. If it's con-rotatory, we're going to rotate our thumbs in the same direction. If it's dis-rotatory, we're going to rotate our thumbs in the opposite direction, right? Let's do an example of that now. Let's do this one. Okay, so when you see your starting material and it has no wedges, no dashes, no stereochemistry at all, it's all flat and planar, and there is an open ring, right? There's no closed ring yet, then this is going to be a ring closing reaction, right? Where the electrocyclic arrows for this mechanism is going to be this right here. This double bond is going to make a new bond between these carbons right here. This double bond is going to shift over there, and this double bond is going to shift down there. Right. So drawing out the arrows right now, this is what we get so far. Right. And to make it more clear, let's number this 1, 2, 3, 4, 5, 6. Right. In the starting material, carbons 1 and 6 are not bonded to each other. Right. But when I draw those arrows out, we see that we made a bond between carbons 1 and 6, and that new bond right there came from that double bond between 5 and 6. Right. So that's why we see there's a single bond now between 5 and 6. Not a double bond, because we used one of the bonds in the double bond to make a new bond between 1 and 6. And it goes ring around and rosy to get this template there. Okay. So now we see at carbons 4 and 5, these methyl groups are flat and planar because they're on an sp2 carbon, right? They still remain on sp2 carbon in the product, right? Because these are still sp2 carbons. So they're going to stay flat and planar as well. But now we see a problem with this isopropyl group on carbon 1 and this methyl and ethyl group on carbon 6, right? Because carbon 1 and 6 is no longer sp2 hybridized. They are both sp3 hybridized, meaning that there has to be stereochemistry here, right? So now let's do the thumb rule now, right? Because we don't know if the isopropyl group is going to be a wedge, the ethyl group is going to be a wedge, or is the isopropyl going to be a wedge, and then the ethyl group is going to be a dash, or is this going to be a dash? Is this going to be a wedge? Like, we don't know, right? We can't tell just by looking at this. We got to do the thumb rule to help us figure out the stereoselectivity of this reaction. So imagine my eyes are going to be right here, right? And I'm looking down at this new bond being formed, right? We see that this isopropyl group is going away, right? So let me make that more clear of what it means to be away or in, out or in. So this line right here is going to represent if the group is going to go away or inside the pocket, right? This is what I consider the pocket. Okay. So actually, don't think about it like that. Think about it like this. Look at the isopropyl group and the ethyl group in relation to each other. Are they going away from each other, or are they going towards the same direction, right? Are they facing in opposite directions, or are they facing the same direction? This isopropyl group and this ethyl group here. Are they facing the same direction?
I think this inwards, the same direction.
And why do you say they're facing the same direction?
What?
Why are they facing the same direction?
Because it looks symmetrical, that's why.
So this isopropyl group here is not the same as this group, right? Because this group here has only 2 carbons, right? It has only two.
Oh yeah, I
this
didn't
one
see
here has
that.
three
Yeah,
carbons.
yeah,
Right?
yeah.
Yeah. So this is tricky right here because you only look at the very first atom coming off of the system here, right? So the atoms we're focused on is going to be this carbon and this carbon. Any other atoms, because that could trick you, right? It looks like they're going the same direction because like they're facing that direction, right? But
Yeah,
if you start at this carbon and go out there, notice how it's going up like that in that direction,
yeah,
and
I
then in
see.
the
Yeah,
other
I
carbon,
see.
this one's going down,
Yeah.
right? So they're facing opposite direction like that, right?
All right.
Uh-huh.
Got it, I guess. Yeah,
Right,
got
right.
it.
So that's important to know, because if we are ring closing, we're gonna start our thumbs left or right, right? And since we
All
said
right.
that these are facing opposite directions, I'm gonna start my left thumb to the left. Like this is my left side, right? Going to the
Yeah,
left.
yeah,
My right thumb here is gonna represent the other group, right? Let's say the ethyl group. It's gonna face to the right. They're opposite direction, right? This is going to the left. This is going to the right, right?
yeah, yeah.
And I'm starting it my thumbs like this because those groups are opposite direction. Now, how many pairs of electrons do you see that are moving? How many arrows do you see? How many red arrows do you see in this mechanism?
3.
3, right?
Yeah.
So is that an odd number or an even number?
Odd
Odd
number.
number, right, right, right. So we're gonna look at this row here, the 4n plus 2 row, right?
All right.
Uh-huh.
Yeah.
And in the reaction, they gave us heat, right? So we're gonna look at the heat column in the table, which is this delta or triangle symbol, right? And going down, we see that our reaction is gonna be this rotatory. And then this rotatory means that we're gonna rotate the groups in opposite directions, right? And we're gonna rotate it in the direction of clockwise or counterclockwise, right? So let's do that. This is my isopropyl group. This is my ethyl group. What do you want to rotate the isopropyl group? Do you want to rotate it clockwise or do you want to rotate it counterclockwise?
I'm not sure about that, to be honest. I'm not that experienced.
Oh no, that's okay. It's okay. You get to choose. You get to choose. Like this one, it
All
doesn't
right.
matter.
All
You get to
right.
choose.
I'll guess then. Counterclockwise, I
Counterclockwise.
think.
Okay, let's do counterclockwise.
Yeah.
Oh shoot. Sometimes I get messed up. Okay, I have to think about this really quick.
All right. All right.
This is clockwise. This is counterclockwise. Okay, so if I rotate my left thumb counterclockwise, right?
Yeah.
It's a little bit awkward on my hands because this doesn't want to go that way, but the group is gonna go down. See,
All
you see how
right.
it's going
Yeah.
down, right?
Yeah.
If I rotated my left hand counterclockwise, right, Suparna is trying to like break my hand or something. That means that what direction does my right thumb want to go to if we want to rotate opposite direction?
Clockwise.
Clockwise, right? So we're gonna rotate clockwise, like this, right?
Yeah. Yeah.
Right. So now, are they facing opposite direction or same direction?
Opposite.
Opposite direction, right? So to represent that, let's say that since I made my isopropyl group go counterclockwise, which went down, it's gonna be a dash isopropyl, right? The opposite of a dash is a wedge, so the ethyl group is gonna be a wedge right here.
Yeah, because the west is going up, right?
Yeah, the wedge means going up. Wait, did you learn that
Yeah,
already?
all right. I learned that in the course too, that west goes up.
In the videos, or where did you learn this?
From somewhere else.
Oh,
I
see,
don't
see.
remember, but was somewhere else that I learned that.
Yeah, that's good. That's good. Okay, so if that's a ethyl group, that's a wedge that forces this methyl group to be a dash, right? And then it makes sense because we see that if we look at the methyl group and the isopropyl group, they're both going up. They're both going in the same direction. So if
Yeah,
they're both going in the same direction, your thumbs are gonna start here. If you use the isopropyl group and you use the methyl group, right? If you rotate one to be counterclockwise and this one to be clockwise. Wait, hold on. This is gonna be. Wait. Let me see what's going on here. So same
bro
direction.
forgot.
This is 3 pairs of electrons. That's odd. So we want to do this rotatory. Let's make this one go clockwise. This one counterclockwise. Wait, hold on. Did I do the first one correctly? Let's see. So counterclockwise. Oh my god, I did it wrong. wait. I'm getting confused here. Okay, counterclockwise. This one has to go clockwise. What's clockwise? Clockwise. Oh, okay. I rotated my clockwise wrong. Okay. Let's go back. Oh my gosh. So be careful of rotating your groups clockwise and counterclockwise, right?
Ryan, can I see the rule again? Like
Yeah. The table.
Yeah.
Yeah. Right. Here's the whole rule. The hardest part about this whole electrocyclic reaction, in my opinion, is the figure out the clockwise and counterclockwise direction. Right. This you could put in your note card. Like this whole table here, you could put in your note card, and this whole table here. Right. And you just know the definition of con rotatory and dis rotatory. You don't have to put the definitions down. Right. Just know that con is same direction. This is opposite direction. Okay. I messed up on rotating clockwise and counterclockwise. So let's focus on the isopropyl again and the ethyl grin. Right. We said the isopropyl is going to go counterclockwise. That means that the ethyl is going to go clockwise because it's dis rotatory. So clockwise, it's going this way. Right. That's clockwise. Now you notice how they're both going down. Shoot, my brain is gonna break. That means they're both cis, right? So if that's a dash isopropyl, this has to be dash ethyl, right? So I messed up the first time because I made it con rotatory. I made them rotate on the same direction, right? So that makes this methyl group to become a wedge. So if this is the isopropyl, this is going to be the methyl in the same direction. Let's make the isopropyl go clockwise. That means that the methyl has to go counterclockwise because they're opposite direction, right? And then we see that they're facing in opposite directions, making them trans to each other. And this we can say plus racemic. Let me check the key for this just to make sure I get it right before I move on. Let's see. Where is this? Yeah, just be careful of your directions, like counterclockwise and clockwise. Question 18. Oh, I see. Okay, so they said it's gonna be D. Let's see what D is. Yeah, so D right here is the same as what we got. It's just the enantiomer of it, racemic. So this is the plus minus, the enantiomer, right? These are enantiomers of each other, right? Everything flips, right? Isopropyl, ethyl flips to wedge, and methyl flips to dash. Okay, so yeah, you can stick with these tables here to figure out these electrocyclic reactions. Okay, so compound is D. It forms in a disrotatory manner, which we said earlier, disrotatory, and will be racemic, right? Which is what we just went over, the one-to-one mixture of enantiomers. Further reaction to the product of the above reaction with light will give compound. Okay, so let's do that. So what that's asking for is that we're gonna react this molecule in light. Right. Which you can see as that symbol right there. Okay, so let's do the same technique, same process, right? Now, the first thing you do for these types of problems is figure out if you have a ring opening or ring closing reaction. So if you see stereochemistry, like wedges and dashes here, and you already have a ring, then that's the biggest sign that you're going to do a ring opening, right? Because we already have a ring here, and we have stereochemistry here. So we want to open up this ring, right? The arrows of ring opening are trickier than the arrows of ring closing, right? Because these are going to be the arrows here. We're going to shift that double bond there. This single bond here is going to break and make a double bond right there. That's the tricky arrow right there, right? This arrow here is starting from a single bond and going to another single bond, right? It's breaking the single bond and going to make a double bond right there, right? That's going to shift this double bond over there. So those are the arrows of this electrocyclic ring opening reaction, ring opening, right? Be careful of this arrow here, right? It's not starting from a double bond, it's starting from a single bond. If we draw out the template, this is what we get. Right. Wait, we're back. Someone's knocking. Yeah, I'm back. I got grapes. Yay! Let's go. Uh-huh. uh, so juicy. Okay. So to make this more clear, let's number this 1, 2, 3, 4, 5, 6. Is that 1, 2, 3, 4, 5, 6 chain? Is this 1, 2, 3, 4, 5, 6 chain after we open up the ring? Right. We broke the bond between 1 and 6. Wait, there's no more bond there between 1 and 6. That bond went here to make a double bond between 5 and 6, and it went ring around the rosy again. Okay, so at carbon 4, we see that this methyl group stayed on an sp2 carbon, so it stays flat and planar. We don't have to worry about the stereochemistry of that, right? It's not wedge, it's not dash. But we do have to worry about the stereochemistry of these 3 groups here, right? Because it came from an sp3 carbon to an sp2 carbon, right? So they're gonna be flat as well, right? But how do we tell what direction they're in? Is it gonna be like this, like how it was originally, or is it gonna be like this, or is it gonna be like that, right? There's a lot of different combinations that it could be, depending on what our conditions are. So let's do that process again. How many pairs of electrons are moving in this electrocyclic reaction? I don't think about the 4n+2 or 4n rule. I think of the number of electrons, right? 6 electrons are moving, and that would be 3 pairs of electrons, right? To use this table right here, we think in pairs. We don't think about the individual electrons, we think in pairs, right? So 6 electrons would be 3 pairs, which is an odd pair of electrons. So we're going to look at this row here, right? Which is 6 electrons, or 4n+2 electrons, or an odd pair of electrons, 3 pairs of electrons. You could see that by these 3 arrows here, right? The number of arrows you see is going to be equal to the number of pairs of electrons in the reaction. So that's a faster way to figure out if your reaction is going to be con-rotatory or dis-rotatory, right? So 3 arrows, odd pair, boom. Light, con-rotatory, right? So our reaction now is going to be con-rotatory. Okay. Now, we are ring opening now. So we're going to start our thumbs up or down, right? Based on the wedge or dash. So we see here that this isopropyl and this ethyl group is going up because they're both wedges, right? So they're both going up like that. This is the isopropyl. This is the ethyl, right? And since we said this is going to be a con-rotatory reaction, they're going to rotate in the same direction. Let's say that the isopropyl rotates clockwise. That means that the ethyl would also have to rotate clockwise because they're gonna rotate in the same direction since they are con-rotatory, right? So clockwise, clockwise. Okay, so they're gonna face in the same direction. They're going to the same direction, right? So to draw that out, let's draw it like this, same direction. And there's two ways that we could draw this at. We could draw the same direction as this, where the isopropyl group is going up, right? Because we look at the first carbon that's going up, the ethyl group is gonna go up like that as well. We could draw in that form, or we could draw it in this form here. Boom, 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 and then boom, boom. Right. We're not worried about the methyl group yet, but right now, what do you guys think is more stable? A or B right now? Which one looks more stable?
A, I think. I don't know.
Oh,
I
yes.
think it's A.
Yeah, it is A. But do you know why, or was that a guess?
I don't know why this question it.
Yeah, it looks more nice, right?
Yeah, it looks more nice and stable.
Why does it look more nice? What's wrong with B? Why don't you like B?
No, I mean the semicolon looks nice, not you.
Right, because it's like too crowded, right? Like too
Yeah,
too much
it's
stuff
too
going on.
crowded, you know.
It's
Yeah,
crowded. Right.
yeah.
What we call that crowdedness is steric hindrance. Right. It's just bumping into each other too much. Steric hindrance.
All right, so
Right. So that's not good. We don't want that.
yeah, and that make it more unstable, right?
Less stable.
I
Yes.
I said more unstable. Yeah,
Right.
yeah, you
Right.
know.
More unstable. Yeah, you're right. More unstable.
Yeah,
Less
that's what
stable.
I meant to say.
Yeah, nice. Yeah. So that makes this one less unstable or more
Yeah,
stable. Yeah.
yeah,
Right. Because of less steric hindrance, less crowdedness.
yeah,
Right. Okay. So now let's look at the isopropyl and methyl group. They're in opposite direction. So let's say this is the isopropyl group. This is the methyl group.
methyl group.
Right. Oh, I mean, yeah, methyl group. Right. This is conrotatory. So let's say that I rotate my isopropyl group clockwise. This would also have to go clockwise. Right. Now they're facing opposite direction. Right.
Yeah,
My isopropyl group is going on the right side. My methyl group is going on the left side, opposite direction. Right.
yeah,
So to draw the opposite direction, the methyl group is going to be right here. And it's forced to go there anyway because the ethyl is already taken. But to confirm that, it does make sense, right? This methyl group is going down. This isopropyl group is going up, opposite direction. Right.
yeah.
Let me double check the key on this. If the key also had this as well, just before we move on.
All right.
Okay. Compound B. What's compound B? Yeah. Let's go. We got it. Same thing here, right? So ring opening is tricky in two ways, right? It's tricky in that you have this weird arrow right here starting at a single bond. And it's tricky in that when you say that the isopropyl and methyl group are going in opposite directions. Yeah, opposite directions right here. Oh yeah, same direction, same direction. Right, the isopropyl group and ethyl group are going in the same direction. There's two ways that they could go in the same direction. They could go up or down, right? You have to see which one is more stable and then stick with that one, right? Ignore the unstable one. So that's why ring opening is going to be harder than ring closing, right? Ring opening is harder because there's more things to consider. Okay. Yeah. So compound B, further reaction of the original products with heat will give. Okay, so they want us to do this again, but okay, let's speed run this one now. So they want us to react B with heat. Let's. So yeah, I think you guys get the process. React this with heat. No stereochemistry. This is ring closing. Here's the arrows for ring closing. Let's make it clear by numbering this 1, 2, 3, 4, 5, 6. The template. Boom, 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 boom. That's this 1, 2, 3, 4, 5, 6 ring closing. At 4, the methyl group stays as a flat planar bond because it stays on an sp2 carbon, right? And carbon 5 as well. Carbon 5 is also flat and planar because it stays on a flat it stays on the sp2 carbon, right? Okay, now let's look at the isopropyl group and the ethyl group. They're both facing in the same direction, right? And since we are ring closing, we're going to start our thumbs left or right. And since we see that we have an odd pair of electrons participating in the reaction in, what was it, heat? In heat, then our reaction is going to be this rotatory. It's going to follow this rotatory manner. This rotatory. Okay. So this is my isopropyl group. This is my ethyl group. They're facing in the same direction, right? Because we see that they're both going up. But that doesn't mean you start your thumbs up, right? It just means that your thumbs are going to go in the same direction. Our thumbs are they going to be left or right? Right. So I'm going to go this way, same direction. Let's say that I make my isopropyl group go clockwise, right? Clockwise. That means that my ethyl group has to go counterclockwise because we are this rotatory, opposite direction. So counterclockwise, not this way, right? This is counterclockwise. So once we see that the isopropyl group is wedge going up, the ethyl group is dash going down. They're trans to each other, right? So to draw that, this is what it would look like. The isopropyl is going to go up. The ethyl is going to go down, right? It could have been the other way as well, right? Depending on how you've rotated it, the isopropyl group could have been a dash, the ethyl could have been a wedge, right? Which is the enantiomer of that. I'm just going to say right away that the methyl is a wedge, right? Because that's the only place it could go to. But let's make sure that it's a wedge. This isopropyl group is going up. This methyl is going down. Opposite direction. This rotatory, clockwise, counterclockwise, right? So if we rotate this rotatory for the isopropyl and methyl group, we see that those two groups there are cis to each other. They're both facing up, which is the case in here, in this thing, right? See what they say. 18. That is going to be compound A. Let's see what A is. Wait, what? Further reaction, we give compound A. Further reaction of the original product with heat will give compound A. So was it not asking for this? It forms this sort of manner. Further reaction of the products of the above reaction with light will give compound B. We got that one. B. Further reaction of the original products. Oh my god. I started with the wrong reactant. So this wasn't the original product. This was the second product. Right. So if you reacted this with the second product with heat, this is what you would get, right? But the problem set wasn't asking for that reactant. Yeah. So I started with the wrong reactant. The question was asking for for what, let's say, where was it? For the reaction of the original product. This one here. It was asking for this one as the reactant in heat. Okay, so let's do that one. But that's good. We did extra practice. But did that make sense to you guys? Like when I went over that extra practice that wasn't asked in the problem set? Okay, that's good. That's good. So read the question carefully. Right, I would have lost points there. Right. So the question is asking specifically for the original product of the reaction. This is the original product of the reaction with heat. Okay, so we could do that, this, and that. Right, this is ring opening because we see it's a ring already. We see stereochemistry. The template is going to be like this, right? Let me make it bigger so then you guys can see what's going on here. Boom, boom. 1, 2, 3, 4, 5, 6. Once you guys do enough practice of these, you guys can skip the numbering part, right? And then you guys could just see that this backbone here is that backbone right there. But once you guys start practicing, to keep track of everything, I recommend numbering it so that you don't put the group on the wrong carbon, on the wrong spot, right? The methyl groups on carbons 4 and 5 will stay as flat and planar because they stay on a sp2 carbon. Let's look at the isopropyl and the ethyl group. But before we do that, we have to determine if this is con-rotatory or dis-rotatory. Heat and 3 pairs. Heat and 3 pairs. Heat and an odd pair. Dis-rotatory. 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 Okay, so this is a dis-rotatory reaction. So let's say my isopropyl is this one. My ethyl is this one. If I rotate my isopropyl clockwise, right? This is clockwise. And that means that this ethyl group has to go counterclockwise because this is dis-rotatory, counterclockwise. No, this way. Right. Okay. So the way that I rotated it right now, that's one version of it, right? Where they're gonna go into each other like that. They face into each other, right? One is yeah, they're gonna face into each other. So let's just write that down right now, which is gonna look like this. Boom, boom. So that's one of it. The other one is gonna be if I rotate my isopropyl counterclockwise and my ethyl clockwise, right? Now they're facing away from each other. So it's gonna go like that or like that, right? They're still opposite direction in both cases. This isopropyl here is going down. This ethyl here is going up in this example. In this example, isopropyl is going up, ethyl is going down, still opposite direction. But which one do you guys like better? Which one looks more stable? Yeah, the second one, the right one, less steric hindrance. So ignore that one. You guys don't have to do the methyl one if you guys get this one correct, because the methyl one is just gonna be in only one direction up there, right? But to make sure, right, isopropyl, methyl, dis-rotatory, counterclockwise, clockwise, right? Where they're both facing in the same direction. And in this case, it is facing in the same direction, up and up, right? Look at the first atom attached to the system, right? Don't look at the other atoms, ignore that. Because some people look at that and then they get the wrong direction. Look at the very first atom attached to the system, right? So that should be the answer, right? Which is A. Yep, it is here. There you go. Okay. So that is A. If we change heat to light, the major product of this reaction okay, so that's another practice problem. If you change heat to light, concentrate the respiratory, these are okay. This is the this one here. Okay. So let me read this question. Change the heat to light. Heat to light, the major products. Okay, I think this is referring to the original problem here. Yeah, okay. So let's do that. So this time we're gonna react it with light. Oh, light. Ring closing, boom, boom, boom. Odd pair, light. Odd pair, light. Con rotatory, con rotatory, con rotatory. 1, 2, 3, 4, 5, 6. Wait, what? Is it density? No, there's no double bond there. Single bond. Okay. 1, 2, 3, 4, 5, 6. Okay. 4 and 5 methyl group stays planar. Now, this isopropyl group is going up. This ethyl group is going down. Right? And if we are ring closing, we start our thumbs left or right. Right? So because this isopropyl group is going up, this ethyl group is going down, don't start your thumbs up or down, right? Because we're ring closing here. Start our thumbs left or right. I'm going to say that my isopropyl group is going to the left side. My ethyl group is going to the right side, right? That shows that they are opposite direction from each other at the beginning, right? Because we saw that isopropyl was up, ethyl was down, opposite direction. Isopropyl is left, ethyl is right, opposite direction. Conrotatory, so let's say my isopropyl group goes clockwise, my ethyl group would also have to go clockwise, right? So we see that they are trans to each other. Isopropyl is wedge, ethyl is dash, right? So what that would look like is that isopropyl would be a wedge here, and ethyl would be a dash. Another common misunderstanding that students make is that when they figure out that this is a con-rotatory reaction, they think everything is cis, right? So they would make this a wedge, they would make that a wedge as well, or vice versa. Make that a dash, make this a dash as well. But that's not what it means, right? Con-rotatory is describing how you rotate your groups, right? So first you determine where they are relative to each other, they're opposite, and if you have to rotate them in the same direction. That's what con-rotatory and dissociatory means. Clockwise, clockwise. They end up trans to each other, which is why they're trans to each other here, right? And that's gonna force this methyl to become a wedge. But let's just make sure, right? The methyl and isopropyl are going up, right? But we don't start up. We start left or right because we're ring closing. So let's do this way. Con-rotatory, clockwise, clockwise. Same direction. In this case, they are cis to each other. They're both wedges, right? And you could say racemic as well. Okay, let's see what the key puts. 18. C. They said C was the major product. Yeah, we got that. Okay. Same thing, right? The methyl is wedge. Same thing. Okay. C. Conrotatory, rotatory, conrotatory, racemic. Are these called electrocyclic reactions? How Levens calls it? Let's see. Electrocyclic. Yeah. electrocyclic reactions. Okay, so that yeah, this problem here almost took up the whole office hours, 50 minutes. That was so much, but I had to like give you guys the table to put on the note card, counterrotatory, disrotatory, even pair of electrons, odd pair of electrons. Like what counterrotatory, disrotatory even means, the thumb rule to predict the product. Yeah, let's go over the table again. This time, I want you to practice this. Right. Let's do this here. Let's do this practice problem. And then I'll ask you questions to guide you through this. And then we'll end the office hours with this problem here. So we didn't get another place, but we'll do this. So that's a butyl. Let's say this is a methyl. Let's say this is isopropyl. Let's say this is light. And then whatever product you get, you react that with heat. Okay. Yeah, I'm glad this helps on the electrocyclic reactions, because sometimes students get confused on like how to approach these problems, like what's wedge, what's dash, well, like if it's flat, what direction does it go? Does it go up, down, what direction, right? Okay, so let's think about this problem here. So the first thing I do is determine if this is going to be a ring opening or ring closing reaction in the first place. What do you think this reaction would be? Ring closing or ring opening? Ring closing, because we don't have any stereochemistry and no ring to begin with, right? So yeah, welcome back, Gavi. How many arrows would you predict for this ring closing mechanism reaction? Electrocyclic ring closing mechanism. How many arrows would you expect? 2 arrows, right? One right there, that's gonna form between these carbons, form a bond between those carbons, and then another one right there. Those are the 2 arrows of the reaction, right? So let's number this 1, 2, 3, 4. We're gonna make a 4-membered ring here. Which this is 1, 2, 3, 4. Right. This new bond between 1 and 4 was made from that double bond between 1 and 2. Right. And then it goes ring around rosy. The double bond between 3 and 4 makes a double bond between 2 and 3. Okay. Let me add something extra here. Let's say at a carbon 2, there is an ethyl group. What would the stereochemistry of the ethyl group on carbon 2 be here? Would it be wedge, dash, or flat and planar? Yeah, flat and planar, because it stays on an sp2 carbon. Yeah, nice. So ethyl group says flat and planar. Now, we see at carbons 1 and 4, it used to be sp2, but now it's sp3. So to determine if we have a conrotatory or disrotatory reaction for the stereochemistry, what 2 things do you guys have to look out for, like for the table, right? What 2 conditions do you guys have to look at to determine if this reaction is going to be conrotatory or disrotatory? What 2 factors are you guys looking for? Yeah, light or heat on the arrow, and how many pairs move? How many pairs of electrons move? Or how many arrows do you see in this reaction, right? So we see 2 arrows or 2 pairs of electrons are moving and light, right? 2 pairs is an even pair. So we look at this first row here. We have light, so that's going to be this rotatory, which means that we're going to rotate the groups in opposite directions, right? In terms of clockwise or counterclockwise. So this is a dis-rotatory reaction. Okay. Now, what 2 groups do you guys want to compare first? We have this turbutyl, which is the group that we have to choose for this carbon here. But for carbon 4, what group do you guys want to use to compare with the turbutyl? The isopropyl or the methyl? It doesn't matter. What you guys choose. Isopropyl. Okay, let's do the isopropyl. Now, between the turbutyl and the isopropyl, are they going in the same direction or opposite direction? Opposite direction, right? So don't think about it in terms of up or down. Think of it in terms of opposite or same direction. They are going in opposite direction. So when we do the thumb rule here, table here, we said that we are ring closing. We start our thumbs left or right, right? So we don't start our thumbs up or down. We start our thumbs left or right. Let's start the turbutyl on the left hand, left thumb to the left. And let's start my isopropyl group to the right, on the right thumb. Since this is dis-rotatory, I'm going to make my left thumb go clockwise, right? Now, where would my isopropyl group go if my turbutyl went clockwise? What direction would my isopropyl group go? Counterclockwise, right? Which is not this, right? Because that's clockwise. It's going to be this, right? Now, we see that these 2 groups are facing on the same direction, facing up, right? So this turbutyl here has to be a wedge, and this isopropyl group here has to be a wedge, or both dashes, right? So this rotatory here does not mean that these 2 groups will be trans from each other, right? We saw that these 2 would be cis to each other. And then that automatically makes my methyl group a dash, but let's make sure. The turbutyl and methyl groups are going in the same direction, so they're both going to go left. Let's say the turbutyl goes clockwise, the methyl would also have to go, the methyl would have to go counterclockwise because this is dis-rotatory, right? So now we see that they are trans to each other, which makes sense, which matches up here. Right, so that's the product of the first reaction. Okay, let's do the second reaction. We're going to use that product that we just formed and react it with heat. Okay, now what would this electrocyclic reaction be? Ring opening or ring closing? Ring opening, right? Now, how many pairs of electrons do you think are going to move? How many arrows are you going to draw in this ring opening reaction mechanism? Right, so this right here is a tricky one, right? Because where would you say your 3 is? How would you describe your 3 arrows? What bond do you want to start with, and where do you want it to go? Yep, if we break the bond connecting them, which is this bond.
Hey, wait, I'm so sorry. I counted wrong. It's 2. I didn't realize that when I was drawing it on my iPad, I drew the pi bond in a different location, so I had 3 moving and I was confused. I'm so sorry. It's 2.
No, it's okay. It's okay. Right. But did you make this a cyclo like butene here, like the 4?
Yeah.
Okay, that's good.
No,
That's good.
yeah.
Right. And did you draw your 2 arrows?
I think I miscounted the arrows. I think I drew an extra pi bond. I don't know how it got in there.
Oh, an extra pi bond, like this?
No,
or...
I accidentally drew it. I was like
Oh.
moving different things. I was like, oh, why do I have three? Okay, my
Right,
bad.
right, right. I know that's like I made that mistake too earlier. Like when I was doing this, like when I made that new bond between 1 and 4, I put a double bond between those two atoms, but it's a single bond that's being formed, not a double bond. Right. Right. That's good. So this is what it would look like for the two arrows. You could number this 1, 2, 3, 4, and when you open up that 4 carbon ring with the arrows, this is what you would get: 1, 2, 3, 4. Right? You see a double bond between 1 and 2, and 3 and 4. Right? Now, what would be the stereochemistry of the ethyl group on carbon 2? Yeah, still flat because it stays as an sp2 carbon. Okay, right? So flat like that. Now, our carbons 1 and 4, they turn into sp2 carbons, but we don't know the direction of the groups, right? If they're gonna go like that, like this, or any other combination, right? So let's do the same technique. We saw 2 arrows and heat, right? 2 arrows, that's an even pair, which is this one, and heat. So that's con rotatory this time, right? Using that table, the first table here, to determine if it's con or dis-rotatory. This is con rotatory. Okay. Now let's use the same groups, tert-butyl and isopropyl. We see that they're both facing up, same direction, and since we are ring opening, right? We are going to start our thumbs up or down, right? So my tert-butyl is going to be up. My isopropyl is going to be up because they're both wedges right now. Since this is con-rotatory, if I rotate my tert-butyl to the clockwise direction, right, then my isopropyl would also have to rotate to the clockwise direction. So we see that they're going in the same direction, right? So we could go 2 ways to go in the same direction. Tert-butyl could go down, isopropyl group could go down, or tert-butyl can go up, and isopropyl group can go up. Which one do you guys like better, the left or right one to keep? Yep, the ones going up. Right. Right. The right one where the 2 groups are going up the same direction because that avoids steric hindrance. And then I think you guys get the point now. The methyl group would just go down there, but to double check, tert-butyl up, methyl down, con-rotatory. If tert-butyl goes clockwise, methyl would have to go counterclockwise, which is this way. Right? Oh wait, yeah. Wait. I messed up one again. Clockwise. Oh, and then it's con-rotatory, not dis-rotatory. Con-rotatory, so it has to be clockwise as well. Clockwise. Right? Now they're facing opposite direction, which matches up here. Right? Now they're opposite direction. So that's going to be your major products here. Right? Be careful of the clockwise and counterclockwise direction. Right? And con-rotatory and dis-rotatory. Yeah, so that's it for electrocyclic reactions. Any questions on this part? Is the process of predicting this make more sense now? Did you guys do something similar like this when you guys were predicting electrocyclic reactions, like ring opening, ring closing, or how was your guys' method? Like how did you guys approach these problems? Like you just guessed like if it's gonna be wedge or dash, or like where the groups are gonna go, like up or down. Like you just guessed like where it's gonna go. Yeah, right. So yeah, this is a more of a clearer like pathway to approach these. You could say racemic here, right? Because you could get the enantiomer version of this as well. Yeah. Okay.
Ryan, I had a quick question. It's not related. I don't know if it's related to this, but do we have time to answer it, or should I wait till tomorrow?
Let's see what it is first, and then if it's a quick one, we can answer it. But if I think it's gonna take like some time to explain like the concepts behind it, then we could continue tomorrow.
Okay. It was just something called like highest occupied
Oh,
molecular orbital. I don't know what that is. Somebody explained it to me and I was just really confused, and I think it has something to do with like how they rotate, but I'm not sure. And I was wondering if you could explain it. It's totally fine if you can do it tomorrow too.
right. And that's relating with the Diels auto reaction, right? The highest occupied molecular orbital, or HOMO, and LUMO, lowest unoccupied molecular orbital, right?
Explain
HOMO
it
and
with
LUMO.
the disrotary and
Oh, for the
conrotary.
disrotary and counterrotary electrocyclic reactions.
Yeah, I think
Yeah.
with
So
that. I'm not sure.
yeah. It does have to do something with that as well, like the HOMO and LUMO of the electrocyclic reactions, right? But you didn't have to think about that when you predict the product, but it will show up in the vocab. So I can go over like the concepts of that tomorrow, right? Because it's really
Okay.
it take a while for me to explain the whole concept from the beginning.
Okay.
Huh?
No worries.
Yeah,
Thank you.
no problem. See ya. Okay. No problem.
Hello?
Hey.
Long day?
Yeah, long day. I just finished my two exams today. It went well. I passed. Let's
Nice.
go.
Nice.
Let's go.
Good.
Mhm,
Good job.
mhm.
Is it okay if you like show your answers for your exam?
Mm,
If it's
ex-
okay?
my answers. I don't have the answers to it. The professors keep it for some reason, so I don't have the copy of my exam.
Rape.
Mhm.
So I will never know the answer for your exam, lol.
Yeah, I know, I know.
Lol.
Uh, 18 push-ups. Let's do it.
Oh, yeah.
Let's do it, Davi and Ryan. Let's do it together. Come on.
Okay. I just.
Alright.
Let's do
You
it.
can't hear me though because I'm using my headphones.
Okay.
I'm already on the ground.
Okay. 3, 2, 1. 1,
1,
2,
2, 3, 4, 5, 6, 7,
8,
8,
9,
9,
10,
10,
11,
11,
13,
12, 13, 14,
15,
15,
16, 17,
18,
18.
20.
Oh, Ryan's still going. He's
I'm
crazy.
going. You know, my school had club rush today,
Uh-huh.
and they brought out the pull-up bar.
Mm.
There's like how many, like 15 pull-ups, you get a water bottle. I was
Mhm.
like, I really wanted that water bottle, but the thing was, I only got 14 pull-ups. It's like,
Oh,
damn it.
I
that's
barely
good.
can't do them. I barely can't
Pull-ups.
do the push-ups. It's really exhausting.
It's a lot of body weight exercises. How much do you guys weigh? Like, can you guys carry your own body weight?
125.
125. That's good.
I
That's
will
good. That's
start
pretty
beside
good.
almost a weight.
Uh-huh. What was your weight, Davi?
64 kilograms.
64 kilograms. How many? How do I can't read kilograms? 64 kilograms. 2 pounds. 141 pounds. Dang.
Hmm.
Yeah. So it's hard to carry your own body weight, huh?
Yeah, it is.
Yeah. Dang. Electrocyclic reactions. Okay.
I've been like sitting at this desk for like 4 hours, just like like doing homework, and I wanted a break, but I
Uh-huh.
have like 2 tests tomorrow.
Oh, you have two tests tomorrow, just like how I had two tests today.
Yeah.
Oh my God. Good luck. How are you feeling about it so far?
It's like they actually have notebook checks, instead of just like, since like in college they don't really check you for notes or whatever.
Mhm.
My class is just like you give your notebook and then they grade you also on that.
Uh-huh. Dang, that's crazy. Like notebook, homework.
Yeah, 60% of my grade is quizzes and tests on like ones I've
Oh dang.
When will senior semester classes start? I mean, work hours.
wait, what?
When will senior semester work hours will start?
Workout?
No chemistry office hours.
Yeah, senior semester office hours.
Uh, these office
Still,
hours are more for organic chemistry.
yeah.
So we will have organic chemistries continuing when
Yeah,
organic
so I
chemistry
still a lot of organic
continue.
chemistry, not anytime soon, right?
Yeah, right. But I
I
do
say
plan.
né for some reason. That's the Portuguese variant. Você will say okay,
Uh-huh.
That's the Portuguese way of saying okay.
Right. But I do plan on expanding my tutoring services and learning high school chemistry, AP chemistry, general chemistry in college, and then biochemistry because I already took all of those
It's a
classes
lot
before.
for two people.
Yeah, I know.
Not a lot
For
of people
you,
would like want to study just because they saw a YouTube ad on school.
for
Right.
you.
Right. I can do it though. I just have to review it and then I can do it
Mm,
because I already took all those classes. But Ryan, when you take AP Chem, let me know so that we could work on it together.
yeah,
All right.
And
that's
then
a great
Davi,
idea.
you're in middle school. Are you taking any chemistry classes in middle school right now?
What?
Are you taking any chemistry classes in middle school right now?
No, they are not semester class in middle school, sadly. They are only semester class in high school around here.
Oh, but you want to learn very early, huh? Like you already know what a wedge
Yeah,
is and
one
an
low.
acid. You're going so early.
Yeah, I'm learning semester early.
Yeah.
Seventh. Wait, you said seventh?
I'm 17th grade right now, so I'm supposed to be at like 8th grade, but I'm a 7th because mm, I, it's hard to explain.
Mm,
There's school problems, school problems.
School problems?
yeah.
Yeah,
Dang.
it's hard
It's-
to
You got more
explain.
time now.
What?
You got more time. In seventh grade, I was quarantined.
Yeah.
Hmm.
Dang, that's crazy to think about. Like you were a seventh grader when the COVID lockdown happened.
Yeah. Time unwise
When
use.
the COVID lockdown happened, I was
Yeah.
12th grade.
Mm,
Hmm.
12th grade.
Yeah, senior in high school.
Wait, what graduating class were you?
2020, class of 2020.
My sister was class of 2020. She graduated also there.
Oh, did you just graduate this year too, or did she graduate early, like a year early?
Mm, this I don't know. Actually, she's in Sac State right now, but
Hmm.
it's just like when she told me about her high school experience, it was mostly she studied so hard for the SAT, and then the SAT just stopped getting required. It's like, damn.
I know. My sister, she's 3 years younger than me. She didn't have to take the SAT at all to get to college. Like, you don't have to do that too, huh?
Hmm.
Wait, Javi, do you have any siblings?
Yeah, I do. I have three of them. One's my little
Mm.
brother, one's my older sister.
How old are they?
My little brother is 10, and my older sister is 18.
I see.
Hmm.
Mm. You got any motivation? I know you did like two tests yesterday, but it's like I've been studying like the whole day, and it's like, oh my god, like I still have more work to do. But yeah, yeah. Got any
Dang.
more
It
motivation?
is.
Like put yourself in my shoes. Just like I'm a junior. It's like I still have like my microbiology homework, and I have a rough draft that's due tomorrow also.
Yeah. I would like check my energy state, like if I can even function right now to finish
It's
off the
not
problem.
I have a
Like,
high energy, it's just, like, I don't wanna do my work, I wanna use my energy on something else. But it's like I
oh,
still need
right.
the only thing I need to do right now, most important thing is my homework.
Right. So, after these office hours, I would on the homework for 10 minutes, right? Even if you don't want to do it, try to push yourself to do it for 10 minutes,
Hmm.
and then somewhere in that 10 minutes, you will probably like get into the zone, and you want to
Yeah.
keep going. But if
Mm,
not, if after the 10 minutes you can't do it anymore, then I think that's a sign that you need a break
mm.
or something, you know. Yeah, like that's what I would do. I would do first. But you have high energy right now, right? Like, you're not sleepy, you're not tired, you're not anything.
Yeah, I did not take a nap at all, even though I slept at 2 in the morning. I just kept going.
Oh, that's crazy. No caffeine too, no coffee.
No caffeine, no nothing. I didn't even eat breakfast or lunch.
Oh my god. No breakfast or lunch. Oh my god.
And I just drink an entire carton of milk and then just boom, half a gallon and then like some of the food that's downstairs and that's it. Milk really does help. It's better than caffeine in my opinion.
Yeah.
Also, can you say me like same constructor problems on this skeleton? Because I want to practice a little bit with making same constructors, like drawing them.
Oh,
I want
like
to
drawing
practice
structures?
it. Yeah, I want to practice drawing
Practice drawing
structures.
structures.
Yeah.
Let's see. Like drawing bond line structures, like um in
Yeah,
organic
I
chemistry.
can do real simple structures to be honest. I can do real simple ones.
Okay.
I want to
Compounds.
practice them while we are
Blah.
here low.
Here. This is good.
Alright, right.
Here. Do you see that?
I don't see it.
Organic chemistry tutor.
Yeah. On the chat, on the Zoom chat.
Oh, okay. Zoom start.
Zoom chat.
Zoom start, right.
Right,
Yeah.
right.
Hmm.
That topic specifically will help you draw bond-line structures. But if you want to learn from the beginning, you could go to Introduction of Organic Chemistry and then learn those topics from the beginning.
Alright.
This
That's one of
concept
the
is only
resources.
available to members. To access this content, either log in or purchase the site membership.
Oh, really? They make you pay?
Hmm.
That's when
What?
I opened it.
Okay. Don't use that website. Don't use that website then. Let me send you a free one. Let's
Log
see.
in or purchase the free site membership. A
Okay.
membership.
Watch these videos module playlist here. It's gonna go over the general chemistry stuff that you need to know for organic chemistry, right? Like drawing structures. It's gonna show you videos and practice worksheets for you to practice as well.
Study guides. Those structures.
Did you get that link, Davi?
Oh, they're all
Yeah, I
YouTube.
got the link.
Let me see if their worksheets work. Yep. These worksheets are like 3 problems. Let me see.
3 problems.
I wouldn't call it a workbook, but
Yeah. It's just a worksheet, not workbook. Like the PDFs.
yep.
The Jokem one, not the voice link I sent. That's the second link I sent. There's many worksheets in there. 1, 2.
Did Brian, did did you have Google Classroom back then?
Google Classroom? I
Yep.
think so. Yeah. Back then, I remember using Google Classroom.
Like throughout 9th to 12th grade?
So 9th to 12th grade, I think we used something else. Yeah, it was a different website that we used. Oh, it was what was that? School Loop. We use School Loop.
Huh.
But they switched it to Canvas, which is what most colleges use now, Canvas.
Mm.
I think I'll go now. I have stuff to do right now before I go to sleep.
Okay,
I'll
okay,
go and
yeah.
stuff. Yeah.
Let's end the office hours here tonight. Brian will study for his 2 exams tomorrow. Davy will go sleep, and then I will edit the video and upload it to YouTube, and then go sleep.
All right.
Alright.
All right.
Good night, guys.
Good
Good night,
night. Good night.
guys. Good
Bye.
night.
Good luck, Ryan. Good luck. You got it.
Yeah. Thank you. Thank you.